Mas qual que é como que se para frente? O cara não pode ter uma competência. Ele também é finalmente. Я все не фотки там не заборы там что-то где там. Вот. Я взял там вырезал просто на фоне там. Слишком такие фотки, правда, на то туалет. На мой сказал, что я прав.
Поскольку неизвестно, нас смотрят русские или иностранцы. Язык выбирают независимо от присутствия випула.
Она сейчас смотрит. Okay. So today's presentation will be limited. So today we're going to talk about real-time algorithms and temporal data, and particularly about how to store the data and to process the data for further algorithms, for further processing. So we will discuss the fourth chapter of Intuitive Massive Data Analysis work, Formation and Coding of Sciences. And we'll talk about data acquisition and about challenges in data acquisition that this Nation of Coding of Sciences proposed in the article. So, what is real-time data? So, for example, we can consider this case. We have, for example, the CBOE, it's Chicago Options Exchange, and we want to predict some options price. So, what should we consider in this? We should consider some stock market data. We should consider some economic indicators, as gross national product, employment rates, interest rate, and lots of more features. So we have overall a big number of data sources, and we have data coming from these data sources consistently for some time. So continuously, yes, something like that. So let's see real data. Another example, maybe something like streaming of audio data or video data that we want to access somehow store, and maybe therefore process some model trading or performing trading. And so what problems we can face when we always real-time data. So data might be not correct. So either reporting letter without proper care, or maybe it's not gathered yet, so it didn't came yet, so it can be not correct just to somehow process it or somehow process it. Data may not be timed. So, for example, we have two different data sources, and one data source always pushes some data to us, and it's guaranteed that if they will deliver this data in some time, before some time passes. And we have another data source. It doesn't push this data to us. It just it gives us the data per our request, and we can give the data in 1 minute or 2 minutes, or 10 minutes or a second, and even so. Different data sources may have different times, and data may be not timely because it's just not fast enough to meet our needs. Data also can not index, so it was generated, yes, as it's shown on the screen, it was generated without considering the needs of business objectives. Data may not be present, so it may be not present yet. So for a particular period of time, we can face a server failure. So some data source just fails, and we do not get this data. And for example, we may have an announced change in schema together in this data. So in this case, we may have data not present, or it also can be not correct. So this is also a problem that we should consider. And data may not be consistent. So for example, new data sources appear, old one disappears. So if we consider an issue of finding some trends on the internet, some popular topic, well, for example, 20 years ago, Nokia was very popular, and now it's not popular. Apple and Samsung is popular. So, and if we will preserve this feature, like how much Nokia is cited in different articles, well, today it's not relevant. So we should somehow our system should be dynamic. And so how can we cope with this problem? So these are 3 main points that we should provide to our system to cope with some of the topics mentioned above. For example, if we provide our system with eventual consistency, that means that if we have a distributed system, different servers, for example, and we need to push our data to all of the servers, and then sourcing, if we have eventual consistency, we guarantee that this data will be pushed to every server, and it will be guaranteed that it will be there. So, the main idea here is the main point here is an outsourcing, and outsourcing is some set of techniques, is a principle how to build such a system. It's not always, but very often it goes with CQRS approach of building in architecture of some program system. And the main basic ideas here is that it has an event chain. So if we want to modify our object, for example, we provide an event, and then at this event we modify it. We have a chain of these events, and so we have a history of how our object is modified. And so in that case, we may take this history and replay this history on a new server, so we can make a replication. If our server fails, we may have this chain of events replayed again to restore the state of the server before it failed. So we may have some kind of so with this sourcing, we may provide. We may not use data, and we guarantee that data will be distributed to all servers. There is another term, and it's temporal consistency. If we provide our system with temporal consistency, that means that we can provide sufficiently trustworthy data up to time to build materialized view is something like something that's shown to user, or something that we use to payment in some model. Or so it was described in Gold and Johnson how to provide this temporal consistency, and we will describe it, and we will consider it in the next slides. And we also talked about real-time scheduling, the types of real-time scheduling. So what is it? It's like we have server, we have a lot of data sources. We want to pre-process them, store them, and each when data arrives, pre-processing and storing is considered a task. So, and we should somehow understand what tasks should be performed first to provide some result for a certain time t, and which we should delay. So, any questions so far? Okay. We will now consider temporal consistency. So, consider 4 data sources. So we have 4 data sources, and we somehow calculate the result based on these data sources. So here is on the x-axis is the time grows. So for example, at the first moment of time, we receive data from the first data source and the third data source, and it was timely, it was okay. But the second and the fourth were a little bit late. So the second, I can say this, the part of data for the first time we get on the second time. So that means that it's a bit late, and so the fourth data source gave us only on the fourth time period, and so only on the fourth time period we can calculate the result for our first time period. So we should somehow understand how when sufficient data arrived, and how should we calculate this? And this example, so yeah, that's how we provide the data, or to show this data. So in this case, we consider just a simple case when we have 4 data sources, and we somehow count result on these data sources. But we may have a much more complicated case. So we have 4 data sources, we have 2 results. We have 2 results, and in between we have some intermediate results that may be convenient for us to use to build our, maybe to show some of the intermediate results to user, to the client, or just to use them somewhere else in our system. And so also when we process our data to get the intermediate result, in green here I showed the one that is processed fast, and in red is the one that is processed slow. So for example, we have a lot of calculations to get this view of data from data source 2 and data source 3. And in yellow, it's somewhere in between the fast and slow view. So how can, in this case, how can we understand when we should process our data, or what view should be calculated first, and should we calculate the view every time the data source, the data arrives from a certain data source? And to understand this, there are 2 terms: query consistency and update consistency. So here we talk about query consistency. So consider 2 data sources shown on the picture on the right here. So data source A, B, and the view that we calculate based on the sources is called V. So for each period of time, we assign a status. So for example, from the first data source, in the first period of time, we have assigned status closed. And that means that we do not expect any data to come at this particular time, for this particular time. But it may be not complete. So it may be corrupted, it may be not complete, but we can, we at least know that we have this data, we have some data. We cannot guarantee that this data is complete and sufficient for our needs, but we know the status of this data, and we can use this to somehow maybe process it on the next steps. On the second period of time, you see that there is a closed status and complete status. That means that we got sufficiently trustworthy data for this period of time. And we're still getting data for the third period of time. From the V here from the data source V, we can see that it was complete on the first two steps. It was closed on the third step, and we still get from the fourth period of time. And so how can we calculate this? How can we know if we can calculate our view based on these statuses? So we see that for the first period of time, our A data source was closed and B was complete. So we assigned is as closed. So we cannot guarantee that we will calculate it right. So we know that A is not complete. And so we assigned to our view, to the first period of our view, closed. On the second period of time, we see that both of the data sources were complete. So we assigned it as complete. On the third is going to be open because we still get data from the A data source. And on the fourth, we don't know because we just didn't get the data from the A still. So in this case, we see that if we assign to the initial data sources, so in our case, it will be these data sources, these statuses for each period of time, we can then traverse the graph and calculate statuses for each period of time on each view. So we shouldn't calculate it for the whole system. We only assign it for the data sources, and then we can calculate it downwards. So in this case, we may have the statuses, and when we have the statuses, we may know what to do with this data. So Golub and Johnson, yes, Golub and Johnson proposed this idea in their article "Consistency in Stream Warehouse," and they say that it is not. So we may have more than 3 statuses. So these statuses are formed for our needs. So we may have our own and assign it in different situations. So we may have 5, 10, and know what to do if, and we can may have also our own derivation rules for the for our own derivation rules for statuses of our views, and that's why. Well, that's all for this query consistency. So we now know at each particular time what can we do with our data, but we didn't have a solution for the problem that different views may take different time to calculate. So how can we optimize the situation? Here, in this also in this article, Golub and Johnson propose update consistency, and it also is based on this kind of statuses. But now we go not downwards but upwards. We go from results to data sources. So, for example, we know that our result, this result, is computed very slowly, and so we may, here. Yeah, I'll stay here. So our computer is computed very slowly, and we may assign it a status, for example, preferred closed. So that means that if we assign this status as preferred closed, it is very complex to calculate this view, and when new data arrives, maybe we should not recalculate all our view. We should just wait for some time and then recalculate our view in the future. So in this result, for example, is calculated easily, and that's why we may assign the status as preferred open. So that means that we shouldn't reflect our data when it arrived, but it is but this view is easier to recalculate. And that is why we may recalculate or not. It's just a status. This status we can use, therefore, to assign some task, for example. So we may also have another statuses like require open. So that means that our view should reflect the most fresh data that came to us. It should reflect, for example, it's shown to like stock market, this stock market bars. price bars. So this data should be reflected when it came. So we may assign it as require open, and when the data came, we just process it as it came. And also, there's another status, prefer complete. So like we shouldn't reflect the data when it came, but we want to reflect it when it is complete. So when for the first period of time, we know that we have closed connection and the data is complete. And so in our case, for example, we may result the result on the left in red as a require close status, and the result in green on the right as a require open status. We also know that our view, for example, here is hard to recalculate, so we may also assign it. Here I didn't assign it. Okay, so we propose a derivation rule that is described on the right here. So if we have a view and on the path going downwards to the result, there is a require open status, then we should consider it as require open. So here we have from this intermediate result and this result, we have on the path down to the result the require open status here, and that's why I mark it as a require open. So if we go next here, for this intermediate result, we don't have this require opened. Here I have a mistake, not require closed, but it should be prefer closed. We don't have a require open status on this path down to the result. So we mark it as require closed because there is a require closed status in the result. So you can see the steps of derivation here. And for the other intermediate results, here I have require closed because I wanted to assign require closed from the beginning of our algorithm. So here is the require closed, but of course here it should be require open. So to provide the require open for this result, and here it also be require open. But if we, for example, had some prefer complete labels and didn't have on our path require open and prefer closed, we should assign it as prefer complete, and the fallback status is prefer open. So the importance of our statuses is require open, then it goes prefer closed, then it goes prefer complete, and then it goes prefer open in that way. So of course, these statuses also are not constrained, so you might have your own statuses and your own derivation rules, which may be better, for example, in that case. But that was proposed in this article and how they explain it. And as I remember, in the article, they were optimizing the some network. I don't really remember, but they had the reduction of computational complexity. Yes, thank you. Of computational complexity by 30% applying these techniques. So, of course, sometimes you may have strange situations. So, as I shown here, so on the initial state, we didn't mark this table as a require closed because we forget about, for example. And so truly in this case, we would have here a require open. That means that we should reflect every data that comes to our intermediate view. And in that case, it will be computationally expensive to account this intermediate result. But that depends on how you construct this architecture and how you provide the initial statuses. So it won't be success all the time, but is a technique that allows to somehow reduce the computational complexity.
This technique is only useful for database management and constructing queries relational database?
I think no, it can be used anywhere. It's just a concept. So basically,
Can we apply this concept to the MapReduce, for example, paradigm? When we use some different nodes
mhm,
for each computational node, we, for example, propose some partial order
mhm.
of calculations from different nodes to result, and
No, yes, I think it
just
can.
configure a Hadoop system in this way. What the benefit to use this approach?
I think yes, we can do that. Surely, we can provide an architecture for this MapReduce technique, and the benefit will be that, for example, like, well, it's very hard to say because it's a very
Okay,
general question,
yeah,
but I think yes, and we will have. We'll have some optimizations for it. So
okay, so the passage of all this report from the data you have reduced was that there are some challenges in data acquisition, and some scientific people propose different approaches to tackle these challenges in data acquisition, particularly for the real-time computation.
mhm.
But I see that there is one approach proposed. Why only one?
You mean there's not the end? I have.
Oh,
So
okay.
there is continuation. Yes.
So there is one of the approaches which we can use
Yes.
to tackle this problem. And okay, the next question is how we can apply what the systems like where we can apply this approach. For example,
Mhm.
not only relational database, this architecture, but maybe can we use this approach for example, establishing some surveillance system, and we have different video cameras and some latency in data source and some
Mhm.
computation segregation. Okay, so which kind of systems we can apply this approach?
I think this approach can apply almost to every system. So if you have, for example, a solid architecture, I think like not distributed system, yes,
Yeah.
and distributed service. For solid application, I think this is some kind of essential thing. So you should understand when to. So you have some. You are limited with one processor, yes, on one server, and you should understand when to calculate some, when to update your data in the intermediate result or not, and when to just wait and update it further when you have some current calculations done that need to be done right now. So this technique is quite essential in solid application, but even if in distributed, I think it can be also applied. So like, like we may think of a situation Just a second. Well, the same situation. So if we have distributed system, one parts may calculate just easy use, and some parts may calculate the complex ones. And it will take some time for them to calculate. And if we will provide data to the complex use, even if calculation of them is separated on a different server, every time when data comes, it will be computationally complex for the system, for the server to update and to provide the data in a real-time fashion manner. So this kind of concept that can be used almost in every architecture, and I think in MapReduce it also can be used. So we can consider the maps and reduce as this view, and well, for some certain particular issue, we always have some bunch of maps and bunch of reducers, and so when to calculate each of them to provide the most optimal way to calculate them on a particular server, on a system of servers, it's a question that can be answered by this, somehow answered by this technique.
Yeah, okay, I see.
Okay. So then, yeah. So now what we can do, we know we should update our, for example, intermediate URLs. We know how to understand when we have sufficient data to show for further use, but we still not understand how to, for example, assign task for a particular machine to count it to not to miss some deadline, for example. So we should processing of real-time data, we can consider it as a series of deadlines. So for the first period of time, for example, we are gathering data for 5 minutes. To the end of our time period is going to be the deadline. So 5 minutes is our deadline. And so how should we schedule our tasks? So in that case, how can we use this information from statuses that we gathered from the previous step just to not to meet the deadline to provide the answer for the first period of time, for example. So there is a special field. It is called real-time scheduling, and there are some approaches. For example, it's hard real-time. So hard real-time approach systems, they are built in that way that if some task misses a deadline, the whole system just fails. So that means that we failed to provide the answer, and we just don't provide the answer at all. There is another approach of firm real-time, and we don't break the system, but the tasks that miss their deadline, they are just discarded. So they stop their execution, and we just discard it. There is a soft real-time that we don't discard those issues, but we just ignore the results that this issue, this task gives to us. And so in a true real-time data processing, this approaches do not work. So in all situations, we either have the broken system or data will get the inconsistent data, and this doesn't work. So there is another approach, and it is called bounded tardiness scheduling. So task misses the deadline. We not break the system. The task is not discarded, but the tardiness for completion of this task after the deadline is passed is bounded. And so we gave, in this case, we gave some kind of dynamic technique how to provide the scheduling for this tasks. So here we consider earliest deadline first algorithm, the easiest implementation of it, and it is considered to be a bounded targeting scheduling technique. So, for example, we have three processes. For the first process, execution time is 2, and 2 is 1, and 2 and 4 for second and third correspondingly. And periods are 8, 5, and 10 also correspondingly. So, and we should somehow schedule these tasks for them to not to miss their deadlines. So the deadlines here is considered to be a period. So, for example, if we have a 0 time here, so the deadline for the first task is the 8th period. So it should be done up till here. And so for the third and second, the same. There is some kind of coefficient for this earliest deadline first algorithm, and it is the amount of the time that is needed to finish the execution divided by the period, by the deadline when it is when it should be executed. So, in our case, if it, and this parameter shows if it is less or equal than 0, then it is theoretically it is possible to provide such a schedule that none of the processes will miss their deadlines. And so in our case, there is a 92.5% for this coefficient, and that's why we can provide some schedule. But to be honest, this is not really true, because in some situations we may have this U coefficient less or equal than 0, and there is no a way to provide a schedule that no process will miss in deadline. So we will not stop on this here, but there are some situations. So in this case, how can we choose which process to run first? So the name of the algorithm says that the earliest deadline first, so we choose the process that has the earliest deadline. So when on the 0 time period, we look at those processes, and we see that the earliest deadline is for the second process, so it is 5. So we can, so we execute it first. Then on the second period of time, we see when the process 2 finishes, we see that the earliest deadline is for the first process, and so we choose it. Then we choose the third, then we choose again the second, because it is also the earliest deadline than the first, and then again the second, because the deadline for the third process is quite a big. And so this is the algorithm how the earliest deadline first works. And there is a bunch of modifications for this algorithm that eliminates some problems. So for example, in this implementation, if we have processes that are sharing some resources, for example. So in this case, the order of execution of this processes may be significant, and there are some modifications that allow to eliminate this problem. So this is the earliest deadline first algorithm, and we also may have, there is also an earliest pseudo deadline first algorithm. So it's a modification again, as I said, there's a lot of modifications. So that was about scheduling. But even if you provide all of this, query consistency, update consistency, eventual consistency, we scheduled our system that is that never, the tasks never miss their deadlines, you still might have a problem with data integrity. So, for example, ML may be calculated on some view, right? So this may be calculated on the data that is not yet relevant, for example. So if we have, for example, 2 servers, and the write request was sent to one of the servers, and the write event request was sent to one of the servers, well, we have eventual consistency. and it sends the event to another server that you should update some of your views. Then the read event comes to another server, so it somehow processes this data, gives it to the client, and but this but still data from the first server didn't come. So that's the problem. And also we may have some noise, for example, in network, for example, Ethernet. And so how to cope with this problems when we are using our real-time system. So there is a solution, and it's called Paxos algorithm. In fact, it's a family of algorithms and family of protocols. And the main idea here is that different modules of our system, different parts, they provide a quorum, and they reach the consensus in a network of unreliable processors. So the main roles in this system is a client. The client provides the request, for example, write request or read request, and so on. There is a proposer. The proposer is the one who processes the request and proposes the request of the client to our submodules. The acceptor is one of our submodules, and so there are a lot of acceptors. And these acceptors form a quorum, and if they reach the agreement, then the request is processed. And there is a learner. The learner is the one who processes the request. And so it's just kind of a simple concept that I think is used almost everywhere now. Well, people try to use it in their systems, but it is good. With this concept, we may provide this data integrity. And so here is an example of how all of these roles may connect to each other. So the client sends the request to the proposer, and the proposer tells the acceptors to prepare to form a quorum to answer if they will accept this request or not. The acceptors send some information back. It's this information contains some that, first of all, that they are ready to process this, and the second is the last request that they processed. So, and then when proposer gets all the results, it tells the acceptors to accept this request. Acceptors may refuse, reject, and may accept. So, and we may have some, for example, level when, for example, if 60% of acceptors accepted this request, then we can process it. And when they accept this, the request is sent to learner, and we get the response. And the idea here is that we have multiple acceptors from which we choose proposer and from which we choose learner. So all the submodules are equal in roles before we start the process of this Paxos algorithm. And even if one of the acceptors fails, even if one of the learners fails, we still may have the process of accepting or not accepting the request. And that's the main idea. So it's resistant to failures. And here I mentioned Chandra's and Wismer's and Redstone's article, and it's called Paxos Made Live, an engineering perspective. So here, this scientists, yes, they implemented this Paxos algorithm on a real system. So if you wish, you can just read this article to understand how it works better. And so, what are the challenges of the proposal? So, in this article, so we somehow understood how to rebuild a system that is, at least at some point and some level, is consistent to all the problems we discussed. And there was a nice citation from this article from Frontiers in Massive Data Science. The challenge in building large-scale temporal systems is that they must be robust to hardware failures, as well as software bugs. For example, because a modern central processing unit has a failure rate of about one fatal failure in 3 years, a cluster of 10,000 CPUs will be expected to experience a failure every 15 minutes. So if we will distribute a system with a lot of CPUs, we should understand that we may have a lot of failures. And that's where this Paxos algorithm may help us, for example, to provide data integrity and data consistency. So the challenge is that all these algorithms somehow work, but we should understand that it is not the best solution. So as a challenge, they provided a real-time acquisition, storage, and transmission of temporal data. For transmission of temporal data, if you talk about it, so we have 10 gigabit Ethernet is the best as I understand for now, and best is used now in our just life. This is the maximum that we can use. For example, if you want to build a real-time system here in Novosibirsk State University, if you want to build something better, we should use some big servers with optical cables that can provide, for example, terabytes of bandwidth. But this is very expensive, and so this and it is not always used. So, for example, this optical cable that I don't remember, Intel produced this optical cable that has a bandwidth of terabytes per second. Its length can be no more than 5 meters or 10 meters. So we cannot transfer data, for example, from Novosibirsk to Omsk from this cable. So that's also a challenge, how to provide this transmission of temporal data. It's not always meets our network structure, for example. If we talk about storage, well, storage is, I think, for now, it's solved problem. So there is a data centers that we can store it and we can access it. The main challenge here, I think, is that how to read this data in real time. So we can store it, but how to read it, that's the main problem. So if we consider, for example, SSD, it is a flash drive in its essence. It has a very fast read and write characteristics, but if we will read and write from this SSD very often, it will be destroyed. So it's based on semiconductors, and they tend to destroy this, to not destroy, but I can say this. Yes, degrade. They tend to degrade. So in this case, SSD is good, but it tends to degrade, and that's why we tend to low our data consistency when we do this SSDs for a long time. So we should provide maybe some replications. We should provide some copies of our data. But if we want to provide replications, we should transmit our data. And so we again face the problem when we have to transmit the data through some cables and so on. So that is what about storage and transmission. So also the consistency of data. So if we have this, okay, we have this practice, we have this done, but will this solution, for example, scale if we have data 2 orders, 5 orders, 10 orders bigger than the magnitude of audio and video data? Now, at the time when this article was written, I think there was no evidence of this case, and I didn't get this evidence when I was preparing this presentation. So I think that's the open question. And also, it's a lack of effective tools for design, analysis, implementation, and maintenance of real-time temporal time-aware systems. So yes, we also have this lack of instruments still till now. Of course, we have some frameworks, for example, even today, this Hadoop, Spark, and so on, with which we can provide somehow. But we don't have a bunch of instruments that we can apply right here and right now, just for easy use. And that's really decelerate the time that is needed, what the time is needed to produce some software architecture that meets the real time needs. And if we talk about widespread algorithms of real-time data processing. We are the world society is on the step of eventual consistency. So eventual consistency is the most discussed topic now. It's like CQRS and sourcing and so on. So they are talking about this. That's very good and this very fast, and we can optimize it. But even on the time of 2013, they had provided some. The world had the algorithms that can provide not only eventual consistency, but also temporal consistency, and also some real-time scheduling. And so they are used in very narrow, yes, in very narrow fields, these algorithms for now. The only algorithm that become widespread is this event sourcing. And so this is also a challenge because it's very hard, it's for now, it's hard to implement a system that has this event sourcing and to implement a system that has temporal consistency is even harder. So that is what they mean in, I think that's what they mean in lack of effective tools. So there are not such tools that could provide us to build our system fast, real time. So I think that's all for this data acquisition part of first chapter of Frontiers in Massive Data Science article. And so the next time we will discuss the algorithms that are used to process this real-time data. So that's all. I think, yes. Yes, and some references here also. Well, any questions?
Is the Paxos algorithm is only used in Google, or you see that is general?
I think it's only used in Google. It's only used, I think, in, yes, in big and serious like so software systems. I think it might be present in Facebook, for example, or something like that. But it's not widespread, of course. It's not. Maybe even Google don't really need this. In some cases, maybe. So when they are storing some data, so provide some consistency, yes. So it's not widespread. It's just somewhere it's of course used, but we should create instruments that will make these algorithms to become widespread.
Okay. Maybe you could. What, as you see, what from your point of view, what the consequences of the knowledge you have taken from this article?
The consistency.
Yeah, for you.
Consequences, you mean?
Yeah, consequences.
For me,
Conclusions.
some conclusions. Well, yes, good question. So, in fact, I didn't. First of all, I didn't know that this algorithm existed yet, surely. And so now I know that if I want to build a system that I really want to provide some consistent data to store it, I will try to use these algorithms and will try to integrate them. And even if in the nearest future, so in the nearest future, in our work, we will be building a smart system of text recognition, text transcription, and it will go with emotion recognition from the audio. It will go with some milestones recognition from the text, like when two speakers are talking on a business topic, for example. There are also always some milestones. There are some always some emotional stuff. And this is real-time data. So we get this audio in real time, and we should somehow identify these topics, and then all based on these features, we want to somehow provide a clue. Let's consider. To provide some response. So we see this case when CSR, the guy from a call center, for example, that we were close to his client, they are talking, we get this text, we get their emotions, we get their milestones, and based on this information, we want to offer caller from Google what to say next, just to maybe just sell something, and so on. And so this data, there will be, of course, there will be three different, for example, for now, as I understand, emotions, milestones, and text, three different sources of data. And with these three sources, we should somehow understand whether whether emotion that we gather is attributed to some particular time, that this milestone is attributed this for some particular period of the conversation. And so we should somehow synchronize it. And I think in this case, in this system, I will try to use these algorithms to just provide this consistency to get better results in other model learning, something like that.
Yeah, thank you.
Thank you.
Did you have done this presentation? I see that you not only used the report, but also considered some articles. Did you find them from this report?
Yes, yes.
Yes, for the second our reporter. Yes. He said that he's ill.
Sure.
Is that he will that he prepared the presentation, but he can't deliver it. Okay, so we have his presentation, but we'll transfer to the next seminar. And as for our schedule, what we can see, we have next time we'll listen to Artemi, the second part of the report, and yeah, chapter 7, building models from massive data, and we have some proposal for student projects in music composing using deep neural networks. There will be an invited speaker who pose some problems in that. Okay, so we move Boris to the 3rd of May. Ripple, did you select your chapter? Okay, so I'll give you 1 day to select. If you will, if you don't, I'll just say this one, 5th, and that's so you have 1 day to propose your own opinion. That's all.
Okay.
Yes.
Yes, I ask you to write 14 sentences, post it on our workshop website. Right? This is good seminar. I gain good knowledge. So I ask you to send me 2 sentences. Okay. And probably I will publish it. No, I will give you a send.
Yeah,
Okay.
we have a website. Website for the laboratory, and you can click get involved workshop. Oh, it's not last version, right?
It's old version.
So
Until there is last version.
okay, so now we have video translation. You can just students should be there here, but invited people can just use the translation on YouTube. Okay. Okay. Thank you. Спасибо.
Все, процесс остановлен.
М?
Процесс остановлен.